All right. Good evening, everyone. How do you say it in French? Bonsoir?
Yes.
My French is very bad, so I'm not going to say any more, okay? Thank you all for coming. I didn't realize it would be so cold in Brussels right now, so anyways, it's fine. So this session is on cloud cost optimization for Java devs. Is everyone in here a Java developer? Right, okay. Just double checking. Sometimes a Python or JavaScript person sneaks into a session like this and it becomes very awkward, right? Now, before we get started on this, I assume everyone here is running on the cloud in some form. Is that right? Anybody not running on the cloud?
Private cloud, is it?
Yeah, private cloud is good too. Yeah. Which private cloud do you use?
The one from the federal institutions.
Okay, gotcha. Okay, I didn't know if it was running some infrastructure on top. On
OpenShift.
OpenShift, right? Gotcha. Oh, okay. OpenShift is Kubernetes, so you may not like what I have to say about Kubernetes, but we'll get to that in a few minutes. Okay. How many people are running on AWS? Okay, so 3 people. Azure? GCP? Anyone using GCP? Wow, not a single person is using GCP. That's very interesting. All right, so let's get on with this. My name is Pratik Patel. I live in Atlanta, Georgia. I also help organize the Atlanta Java User Group, and we run a small conference there called DevNexus, which is coming up in April. Have you anybody heard of this conference before? Right. So this is the largest Java conference in the US. It's run by the Atlanta Java User Group, which is a nonprofit, and it's very cheap to attend. So I invite you to come. There'll be 2,000 people there this year, and we'll have 14 tracks and people you probably heard of. You may have heard of this guy that has a mustache called Venkat, right? So he's one of the speakers there, for example, and lots of speakers. There's about 140 sessions at the conference. So it's it's as big as DevOps Belgium, which I guess is the local conference, right? Anyways, check that out when you get a chance. Okay, and I do work at Azul Systems. I'm wearing the T-shirt, but it's cold, so I'm going to keep this on, okay? If you don't mind. So we actually have several builds of the OpenJDK. We have a free build that lots of people use. It gets over 100 million downloads a year called Zulu. So instead of using Temurin, for example, or Adopt OpenJDK or whatever they used to call it, you can use that. And then we have a high-performance VM called Azul Platform Prime. I'm not really going to talk about this that much, right? We're going to talk about and focus on, well, just a quick few things our marketing people like this slide. So for Azul Platform Prime, which is our high-performance VM, for example, one of our customers ran Apache Kafka on top of it, and they saw a 30 to 40% improvement in throughput just by switching out the VM, because Kafka runs usually with OpenJDK or some flavor of OpenJDK, so you can swap it out. Anyways, you can also use it to save on cloud costs, which is what we're here to talk about. Okay, so everyone here is running on the cloud in some form, right? So when I think of the cloud and go back to the early days of the cloud, the promise was that with the cloud you get flexibility and you get cost savings. Okay. Now the feeling today is that, are you actually getting cost savings, right, compared to running your own infrastructure? So that's what we're going to spend some time diving into in this session to understand like what all that is about. Does anyone know what this TV show is, by the way? Silicon Valley, yeah. I was working at a startup at the time, and I had to stop watching the show because it was too much like real life, I swear. Okay. Anyways, so here's a question. What's the best way to reduce cloud costs? Not to use it. That is actually true, right? So, of course, the answer is to turn off the servers, right? So everyone probably knows this TV show or movie also. This is Office Space. But it really does depend on your application. That's what I want to dive into in this session, is to go and talk about some of the specific things and general things that you can do. We're going to start at the top with architecture and then go all the way down and look at specific things that can be done. And a lot of it just has to do with how you manage the cloud, to be honest with you. So I'm kind of spoiling the ending here. A lot of it is around management, right? But the real answer is that there's no 1 or 5 or 10 solutions that help you reduce cloud costs. There's multiple different things that you have to do, but it all depends on your application, okay? Now, how many people here run cloud functions, serverless, like AWS Lambda? Anybody? Okay, so a few people, okay? All right, so we'll talk a little bit about Lambda when we talk about architecture or cloud functions in general. Right? So here's some of the topics we'll cover. architecture, what kind of cloud service should you use, or something like OpenShift and Kubernetes. And then we'll get into the nitty-gritty and talk about how this specifically relates to the Java virtual machine and Java applications. All right? So when we think about, well, we'll also talk about over-provisioning, elastic computing, headroom for variable load and all that kind of stuff to kind of round out how we think about the cloud and how we provision, how many instances we have and things like that, right? But let's spend a few minutes talking about cloud pricing. Now, the original promise of cloud cost was that it would go down over time, okay? So we started, whatever, like 10, 15 years ago, a unit of compute, a CPU cycle, whatever you want to call it, the number of, how much it costs to have an AWS virtual server was, substantial. And then, because of Moore's law, right, which is computers get faster and more efficient over time, the premise was that over time the cloud costs would actually go down, okay? But what do you think has actually happened for those people who are on the cloud? Do you think cloud costs I'm just talking about, let's just focus on compute for a second, right, to make this question easier, okay? So do you think that cloud costs has gone up over time, has gone down over time, or has stayed approximately the same over the last 10 years? Anyone want to take a guess? What's that? It went up, okay. That's one of the answers, or possible answer. Stayed the same, right?
For the same power?
Yeah, for the same amount of compute. What do you think?
Then I would think it went down, but...
That's what you would think, right? But there's actually, right, so does the cost of compute on the cloud actually go down? And these are basically cloud pricing anti-patterns, right? Are you ever going to use less of the cloud? Right, the answer to that question is probably no, because you're always building new apps or expanding your application and stuff like that. And if you're running on a monolith, how do you refactor that application? Is the right thing to do to go to Cloud Functions, or to use Kubernetes, or to use a CaaS, which that's like Amazon Fargate and Azure Containers, etc. Right? So this is an interesting chart that I found for AWS pricing over time. Okay, so as you can see, this is only going back to 2019. So this is only about 4 years old, right? Or it only goes 4 years into the past, right? But you could see that over the last few years, the price of cloud has actually stayed the same, or at least for compute has actually stayed the same. Okay, so and the yellow line is memory, and then this is the compute for US East. Okay, and just in general, what the other things like egress and ingress, data costs and stuff like that. Yes?
Sorry to interrupt.
That's fine, go ahead.
This should be indexed compared to bare metal prices, no? Because
I'm sorry, say that again?
this should be indexed compared to bare metal prices, because we can't know.
Right, well, okay. So this chart just shows you how much it costs for compute on AWS, compute and memory. Okay? So yes, you would think that the bare metal would actually, bare metal gets cheaper over time. Exactly, but this is my point, is that even though compute has gotten cheaper at the bare metal, the cost has actually stayed almost the same, right? And actually feels like it's going up.
And is it the same because we still call it one vCPU, or is it really for the same next gen?
Right. That's right.
hardcore?
Yeah, that's right. So when the question is it the same for a vCPU or is for an actual CPU cycle, right? What's the nuance there? Mm-hmm. The short answer to that question is that when you deploy something onto AWS or GCP or to Azure, what they do is they take a fraction of a CPU and they give you that slice of it and they charge you based on that, right? So in effect, you're getting the same amount of horsepower, right? The same amount of CPU cycles, because they don't, yes, they go to the latest Xeon processor or whatever, right? Or they maybe use, what's AMD's large core processor called? It's not Ryzen, is it? Not the Threadripper, it's, I think it's called EPIC, E-P-I-C, right? Right. So, but the basic premise here is that, basic idea is that even though the CPUs are getting faster, the cores are getting faster, you're not getting more horsepower for that, if that makes sense. Because again, what these cloud providers do is they take a vCore and they virtualize the vCore, right? Does that make sense?
Yeah.
Okay. All right, so anyways, the point here is that the cost of cloud compute and memory I mean, you can look at the line for memory too, right? Memory is just memory, right? Yes, it may be faster, but you're not going to like, the memory is not something that you slice up. It's like, I want a gig of RAM or 16 gigs of RAM, and that's how much you get, right? It will be faster, of course, because of the architecture behind newer memory, like DDR5 and stuff, okay? So anyways, oh, actually, one more thing about this chart right here. Ooh, let's go back, okay? Is the only shift that really happened, and this is an aggregate chart, so the only shift that's happened is that when Azure, AWS and Azure launched Graviton, right? Is everyone familiar with what Graviton is? Yeah, Graviton is basically ARM-based CPUs, right? So anyways, let's move forward, right? So when we think of the factors, of course, there's compute, there's storage, there's API calls, there's data ingress and egress, basically moving data in and out of the cloud. All that stuff adds up, and that's what you end up paying, right? Shared APIs, of course, there's databases underneath that, and you pay for everything, right? Nothing is free on the cloud, of course. Okay, so let's spend a little bit of time talking about scaling so that we can understand how this affects basically our cloud costs, right? So here's a little bit of a trick question, right? What's more efficient, a monolith or a distributed architecture?
It depends.
Oh, I knew someone was going to say that. Right. So it's actually interesting because I built these slides a little while ago, about 3 or 4 weeks ago, and just today I saw something on Twitter. Let me see if I put it in here. I'll skip ahead a little bit. There's some research that came out of Google on this very topic, right? And I'll just skip ahead and we'll skip this slide later. But basically, why does Google recommend modular monoliths instead of microservices? Right, so there's a research paper, and you can look this guy up. He points to the research paper. You can download it and have a read of it. But basically, in the abstract or synopsis, they said the prototype implementation, which uses modular monoliths instead of using microservices and something like Kubernetes, it reduced application latency by 15x and reduced cost up to 9x, which is kind of interesting that we're going back to like that monolith type of thinking. But if you read the paper, it has all the stuff that you would expect in that paper about why it's more efficient to use a modular monolith as opposed to using a distributed network, right? It's basically one of the major costs that you have when you have microservices is all the data serialization and deserialization and network overhead that you get from it, right? So when you have a very distributed architecture. Anyways, it's a good paper worth reading. I don't know if I believe everything they say in the paper, but it's worth reading, okay? Anyways, all right, so horizontal versus vertical scaling for the cloud, right? So when we talk about vertical scaling, that's essentially adding CPU and memory to an existing server, right? Horizontal scaling is when we add more servers. So instead of having one piece of hardware that has 16 cores, we have 4 pieces of hardware, virtual hardware, that has 4 cores to get our same 16 cores, right? The horizontal versus vertical scaling, okay? So what's the cost of scaling those two? Right, so the reason why that we moved over to doing horizontal scaling is in this picture, right? So we pay a little bit of a penalty here when we do horizontal scaling because of the overhead and all that kind of stuff, but we get almost a linear line going up so that we can scale out as much as we want at that point, right? Whereas with vertical scaling, at some point, you just run out of the ability to add more cores and more memory, right? Again, it depends on how big your application is, how much load your application takes. So anyways, vertical horizontal scaling. And of course, one of the other problems is that how fast is the backplane or the virtual backplane on a server that you're running. At some point, you reach this level right here where you're at basically peak efficiency, and the more CPUs you add, you're not necessarily going to be able to support more load, okay? So this is kind of basic kind of scaling, and we've been doing this for years, right? But again, this is just a review to set the stage for some of the other stuff that we're talking about. Vertical scaling, linear to a point. Horizontal scaling, linear at scale, right? And of course, the nice thing about horizontal scaling is also elastic. Elastic means that you can add or remove compute, memory, whatever, as you need to, depending on how much load you have. Or at least that's what we think, right? Because what do we normally do? We over-provision and we end up spending more than we need to because we're developers and we don't want our phone going off on Saturday night while we're trying to, not work. So, okay. All right, so let's dip into architecture for a few minutes and look at how this kind of, what the spectrum is, right? So on the far side, left side, you have monoliths, which give you vertical scaling and lots of efficiency if you read that paper that I was talking about, but it's not very elastic. Okay, and on the other side, you have microservices in the middle, containers as a service also in the middle in that kind of area. And on the far right side, functions as a service or cloud functions, which give you the ultimate in horizontal scaling and the ultimate in elastic scaling, right? It's very elastic. Basically, you go to Amazon Lambda or Azure Cloud Functions or Google Cloud Functions, and you say, here's some code, go run it, and just scale it up as much as you want, and then scale it down when it's not being used, right? So, Elastic should provide us the ability to do cost control because it lets us to auto scale up and auto scale down, right? I still don't like Kubernetes because I think it's too complex. That's one of the things I agree with in that research paper out of Google in terms of using Kubernetes versus a modular monolith. They talk about the complexity and being able to do small deployments, which are held up because of interdependencies between different microservices, et cetera, et cetera. Okay, so we already talked about this, so I'm going to skip this. Okay, and in terms of architecture, we have platform as a service, which is just renting a server and then putting your own stuff on it. And then containers as a service, which is basically what I call kind of like managed Kubernetes almost. And then cloud functions in terms of architectural choices that we can make. Okay, so let's talk about this a little bit. There was an article about 6 or 9 months ago out of the folks from Amazon Prime. And they built all this stuff about, I think, 6 to 7 years ago. Well, one part of it. What they were doing is essentially doing transformation on video frames, right? So video frames, there's approximately 30 frames a second, and it's a large amount of data, et cetera, et cetera. So they actually put out a paper saying that they'd switch from doing cloud functions to essentially using containers as a service or just using a platform as a service, basically a standard VM on AWS, right? And of course, everyone who doesn't like cloud functions and serverless hopped in and said, yes, cloud functions are garbage, you should never use them, right? But if you read that, it's online on their on the Amazon or the AWS engineering blog. What they did is they made a mistake up front, which was they were trying to process a huge amount of data that was compute intensive. So when you think of cloud functions, that's the exact opposite of what you should be doing with cloud functions. Cloud functions are good for short duration computes, whatever processing, and they're good for working with small amounts of data. Because otherwise what happens is it becomes very expensive very quickly. Cloud functions can be more expensive. Even though they can scale up and scale down, they can become very expensive, right? So if you're doing video processing, you should just be running it on bare metal if you can. That's the most efficient, cost-effective, whatever you want to think about it, way of running this, okay? All right, so when we think about as developers or DevOps people, these are the 3 key things that lead to having too much cost in the cloud. Over-provisioning is probably the biggest one. Because again, as a developer, we say, you know what, I'm just going to add a little bit of extra to this because what happens when my load goes up, right? How do I handle that extra load? Will I be able to handle that peak, basically, without things melting down? So what do? Our natural tendency in that case is, let's just over-provision it because we don't want stuff to blow up and then our manager to call us and say it's not working, and then you have to go figure out what it is and fix it, right? The other thing that a lot of research has shown is that developers or DevOps people leave VMs running when they're not in use. Okay, so you fire something up, you're running it, and then you just basically forget to wind it down. So that's a lot of where a lot of the cost comes in. Now the third one we don't have time to dive into too much, but the lack of automation around this, right? It basically leads to the first 2. How can we add more automation so that we are more elastic and we don't need to over provision too much, and we make sure that VMs are shut down when they're not in use. Okay, so these are the three big things that we need to address in terms of cloud costs. All right, and the other things are there's oftentimes a lack of governance. And what that means is that you don't have rules or process for what developers are supposed to do for the cloud, right? When they've set something up and when they deploy something in production or just using it in development, whatever. So the lack of governance points to the inability or the lack of a company or a team having proper rules for how they should be using the cloud. Now, as developers, we hate rules, right? We want to be able to do whatever we want, right? But someone, basically, there has to be someone or a team somewhere in the company that looks at that and sets rules for how things are supposed to be used, how they're supposed to be provisioned, okay? And then there's also lack of guardrails. This is where you deploy something, and then all of a sudden, it starts getting used more and more and more, and you don't have a way to protect your, you don't have a way to protect the cost of it because you just let it just keep going, and you rack up extra costs for that, okay? And then, of course, the last one here is that there's unexpected egress and ingress charges. Because as you know, when you move data into or out of a cloud or between cloud instances or between zones, regions, whatever, there's a cost associated with that. And that cost can be quite high, okay? All right, so let's dive into the JVM part of this for a few minutes. All right, so I know Java's not cool anymore, right? Depending on who you ask, right? But Java is actually great for the cloud in terms of efficiency. Right? The power cost ratio or the compute to cost ratio is actually very good. The other thing is that Java is extremely flexible, as everyone in this room knows, in terms of what kind of apps you can build with it. So for example, I think some people said they were using AWS Lambda, right? So did you know in AWS Lambda, they have something called Snap Start now, which is based on CRAC or CRAC. Yeah, it's based on CRAC. CRAC is a way to do essentially instant startup without using GraalVM. Right? Don't use GraalVM, by the way. It's not very good. So we can talk about that at the pub later if you like. Okay, but there are reasons for that. Right? I don't want to go into a long rant about that, so we'll skip that for later. And of course, one language for everything, right? So for Snap Start, the CRAC, all you have to do, and it's only supported in Java. You can build your cloud function, you give it to AWS, you give it to the AWS Lambda console, and there's a button that you can click now that says, I want to use Snap Start, which is essentially CRAC, to do instant startup for this application. Okay, so there's, Java is good for everything from small things like cloud functions now to obviously gigantic monoliths. Okay, so the other thing when we think of JVM in the cloud is that Java actually, because of the JIT, it actually becomes more efficient the more you run your application. Okay, but here's a question for you. Say let's make some assumptions here. Let's say you have a Spring Boot application that has a moderate to high load, and it's a medium-sized application, not huge. Let's say maybe it has 10,000 lines of code or something, right? If we were to put that application under load, and again, this is a medium complexity application, right? Not huge application. And let's exercise this application, under load, production, in your test bed, whatever. How long do you think it takes for the JIT to get to, let's say, 95% efficiency with the code? Because the JIT optimizes code as code is executed, right? How long do you think it takes for the JIT to reach 95% efficiency for that kind of application? 15 minutes. It's not a bad guess, actually. So, anybody else? No? Okay. So it can take anywhere from 15 to 30 minutes. It's the size of the application, the load. We made some assumptions there. So for example, that's what just the standard hotspot VM, that's in OpenJDK. With Azul Prime has its own JIT compiler called Falcon, which does much more aggressive and different types of optimizations. So it actually optimizes the code much better. That can take anywhere from 25 to 40 minutes to reach peak optimization because it's a much more aggressive optimizer. Okay, but that's again in the high performance Azul Prime JVM. Okay, and then of course there's this ramped up time. right? So what happens when the JIT, when you start an application up and you start exercising the code, what happens is it looks something like this. Let me see if I can flip this over without. Okay, so what happens is when your application starts up, the JIT starts kicking in and starts optimizing your code, right? So, what's going on here? Oh, this is turned off. Sorry. Okay, here we go. All right. All right, so you start your application up, it quickly starts using CPU, and then while the JIT is optimizing, it uses CPU, you start getting diminishing returns on this, and then you get that long tail where we flatten out, okay? So this axis is CPU time, and this is just time in this axis, okay? So during this portion of your JVM's process running, whatever, you need to have a little bit of extra CPU horsepower for the JIT to do its work, right? So there's actually something, and I'm going to forget what it's called, on AWS, for example, I think it's called CPU boost. So when an app first starts up, you can say, give it more vCores, right? vCPU, whatever they call it, right? And that can help solve this problem, of course. But, right, so we have this entire area here. So if we provision our server to have this much headroom, this area is, or this portion is what?
Waste.
It's waste. You're paying for stuff you're not using here. Okay, so this is a problem now. Okay? So anyways, everyone is familiar with how Java works at the JIT, but not a lot of people are familiar with that basically that extra CPU utilization while the JIT is working hard to optimize the code. Okay? All right, so let's get back to how Java works, right? So this is, I have the reference here. Unfortunately, you can't see it clearly where this comes from. But some folks did a study on what are the most efficient programming languages, and they have different ones. So the next one is for interpreted languages. So you can see, for example, there's TypeScript and JavaScript over here, right? But you can see that Java is actually quite good. It's very efficient. And what's surprising, or may not be surprising to the people in this room, is that it is about a little bit more efficient than C#, right? So if you look at this, I don't know why Erlang is so inefficient. Does anyone program in Erlang in here? Yeah, I haven't done that in years, so I don't know exactly why that would be high. But anyways, you can see number of joules consumed to do the processing, and you can pull this down and have a look. I apologize for the reference. We'll send the slides out so you can look at these references later, okay? But on this specific graph, Java is like, I don't know, somewhere like right around maybe 40, right? And then if you look, for example, at JavaScript, well, you can't see it on this graph, but JavaScript is closer to almost double the amount of power that is needed to run the same application, right? So they basically wrote the same application and ran it across all these different things. So anyways, some nice charts there, okay? So what are some specific Java optimizations that we can do around this? Right? There really aren't that many, but there are a few things that we can do, okay? So we already talked about, this is the chart I just drew a second ago, this one right here, right? So everyone understands this chart, right? What it means and like the JIT and the warm-up extra CPU. Okay, good. Okay, so right, so if you're running short-lived applications, so for example, if you're running on Kubernetes, or if you're running on OpenShift, or you're using elasticity, this can become a little bit of a problem for Java applications. Because I just said, it takes, for a medium-sized Spring Boot application, 15, 20 minutes for the JIT to reach peak efficiency. So if you spin that up, it becomes efficient, and then you spin it down an hour later, not very good, right? So this is where we have a problem with the elasticity. And then, that's the warm-up time part of it, right? But we want our applications to be elastic, to really save costs. We want it, when we get peak load, we want it to scale up, add more instances, and when we're not getting a lot of load, we want it to scale down, okay? So And then there's also GC pauses, and the hint here is obvious, use less memory, right? And you can't always do that, but you get the idea, right? So when we think about this, is it even worth using the JIT if we're running in a cloud function that gets destroyed every 10 minutes? Actually, a cloud function is not a good example because the code is so small that it'll get optimized within like 30 seconds or something, right? But if you have something that's a microservice, is that long JIT warm-up time even buying you anything really, right? I don't know the answer to this question, to be honest with you. That's something you have to think about with your specific application, okay? Right? So we're not getting much benefit from this JIT, so why even bother throwing CPU cycles at it if it's going to just be spun down, 20 minutes, half an hour after it's optimized, or whatever time frame that you have for your app, okay? So, right, so we already talked about Crack a little bit for that fast startup, but one of the things that we're looking at right now at Azul is so with Crack, what you do is you take a snapshot of the VM at a specific point in time. So can we solve that specific problem, right? So Crack is meant to solve, originally was meant to solve the, let's start the app up very quickly. So instead of a Spring Boot application taking 5 seconds to start, with Crack, a Spring Boot application will start in about 50 milliseconds, okay? So it's much, much faster. It's 2 orders of magnitude faster in terms of startup. But what if we exercise that application and let the JIT get filled up and then took a snapshot of that running VM? Now all of a sudden we have the possibility of having a VM that's running our application that already has a warmed up JIT. Right? So maybe we can get the best of both worlds by doing something like that. Okay? So
The same idea as Crack. Normally
No,
in Crack
it-
warm up
okay.
the VM, and then whenever for a function, for example, it goes down, then you serialize the whole app, you get it back, so you will gain that VM is ready.
Warmed up.
whenever
That's right.
you do it.
Yeah. So
The same idea.
yeah, well, I mean, this is supported by Crack, right? Right now, the current guidance that we give up with people for Crack is that you go and serialize, save the state of the VM. When the application hits, it's ready to service its first request state. So does everyone in here use Spring Boot? Let me rephrase the question. Does anyone not use Spring Boot in here? What do you use? Quarkus, okay. Same thing with Quarkus is great. What's that?
Lucky bastard.
Yeah, lucky, exactly.
I had this question. So
Yeah.
last year with Java was a bit complicated. I left that learning back Micronaut and GraalVM, and now I understand that. So I just do that and keep my existing, just do Crack, and then I load.
Yeah, that's right. So Crack is now, so Crack support for Spring Boot just came out with Spring Boot 3.2, which was released on Thanksgiving Day, basically late November, okay? But you have to be running Spring Boot 3.2, and as you know with Spring Boot 3.2, you have to be running JDK 17. You have to update your stuff. Actually, that's a good question. How many people are running Java 21 in production right now? Okay. How about 17? Okay, that's 11? Okay, one person running 11. How about 8? Anyone running 8 still? Okay, yeah, some lucky people. Well, no, I was going to ask Java 7 also. Oof. Oh boy. Yeah. So anyways, this is one of the issues with using Crack is that you do need to be running JDK 17. So the only commercially supported JVM with Crack support is currently Azul 17 and Azul 21. But it's in our free build of the OpenJDK. So you don't have to pay us to run it. You can just go download it, and it has Crack support built into it, right? But the other thing about Crack is that it only runs on x86 currently. It doesn't run on ARM, so that means it won't run on your M1 or M2 or M3 Mac if you're using a Mac, okay? So it only runs on x86. And that's because Crack uses the Linux kernel CRIU technology, which has been around for a while. Crack builds on top of Checkpoint. What does CRIU stand for? Checkpoint something in user space, right? Anyways, I don't want to get too far down that rabbit hole, but to your question, currently the guidance is get your app to the ready to take a request state, because you don't want a lot of garbage in the serialized, in basically the saved data, the JVM, serialized JVM that you write to disk. So of course what happens when you start exercising your app is you get all these objects created and blah, 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 and you don't necessarily want them. But again, this is something that we're looking at to see if we can warm the JIT up. The JIT does get saved also, right? So we're looking to see if there a way that we can clean out all the garbage objects, essentially do a garbage collection, and then take a crack checkpoint so that we get a fast startup and we get a warmed up JIT, okay? All right. So we already talked about that. Can short-lived apps benefit from JVM configuration? Maybe, right? We might be able to pick a different garbage collector, like using a continuous garbage collector to keep garbage, basically to keep a steady state for our application when we don't have these GC spikes and pauses. Okay, so this is, again, this depends on your application. Azul Prime has a pauseless garbage collector. And the Shenandoah was released with 21, wasn't it? Right, which is another variation. It's not a generational pauseless garbage collector, unfortunately, unlike Azul Prime's C4 garbage collector. But anyways, there's choices there, right, in terms of reducing things for short running. Okay. Now, of course, we talked about the JIT getting more efficient over time. And there are some good GC choices. For a long-running application, I don't feel like you have to spend that much time thinking about your garbage collector, unless you're building an application that has some very high performance and low latency requirements. Okay. So, again, quick plug: Azul Platform Prime. It has a better JIT, so you get less CPU utilization over time. And then we also have something called Ready Now, and Cloud Native Compiler. So, you know how we were talking about using crack to save the JIT? Well, one thing that you can do with this, and unfortunately this is proprietary technology, so it's part of Prime, which is our high performance VM, which you have to pay for. But what these two things can do is you have a server that it optimizes your application with the JIT, but it's not living in the actual servers which are doing your application's work. What it does is it serves up optimized JIT and does its processing over here. So let's say you have an application that's running on 10 nodes. In a Java app, right, let's say Spring Boot again, or whatever, Quarkus, each one of those instances of your Java application will be using the JIT, its own JIT, and using CPU to get optimized, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What if you could just offload all of that to one place and it just serves up optimized Java code into all 10 instances? So basically you're offloading all that CPU utilization into a single place and serving it up, right? So this is proprietary technology that we have that allows you to do this, okay? All right, so this is probably the biggest thing in terms of how do we optimize our cloud stuff, or what's one of the biggest things that we can do, right? Nobody has consistent load, right? Load always goes up and down during the day, right? Or depending on your application, it may be really busy in the morning and then just kind of like this the rest of the day in terms of how much load, how many requests your application are getting, right? So what do we do in this case? Right? And we've talked about this already, but just wanted to review this, right? This is the diagram I use when I'm thinking about, and when I'm working with a customer and I'm trying to help them think about where do we want to fit over here, right? If we're running a monolith, should we over provision? How much should we over provision to capture that peak? And then when we come down like this, right? And how much complexity does elasticity add, right? So we have service level agreements with over provisioning. We can guarantee SLAs. How do we guarantee the same SLAs with an elastic type of deployment, right? And what complexity does that add to it? The answer to those questions is usually somewhere like, well, if we're just running a monolith, it depends on our architecture, then we do a little over provisioning, or maybe we do a modular monolith, or we do a scaled up monolith, okay? But what I like to do for stuff like this, or what I recommend after doing some performance analysis to customers, is that use containers as a service. That's like my favorite deployment model, right? It's not for everybody, I get it. It's not for every application either. But I like containers as a service because you basically say, here's a container that contains my Java app. Just go scale it up and down for me. Here's some rules or some guardrails or whatever that you give it, so that you say, okay, don't scale down if there's not much load after, I don't know, after 30 minutes or something like that, right? So you give it some rules in terms of how you want the CaaS to run, but basically you just hand it to it and then it just goes and runs everything for you. Okay? All right, so there it is. I like CaaS over Kube. The other bonus you get is that it's simpler than running on Kubernetes. You don't have to worry about all that stuff, right? And this is the way I like to say it. Here's a container, scale it for me and handle all the bullshit. So, because I like to focus on writing code, right? I don't want to worry about DevOps and all that kind of stuff. I know that sometimes it's somebody else's job, but anyways, you get the idea, right? And I actually really like Cloud Functions. I think Cloud Functions work really well because they're the ultimate in elasticity, right? We can say, here's something, scale to 0 if no one's using it, right? So we're not paying anything while it's using it. But of course, Cloud Functions are more expensive the more you use them, which is kind of ironic, right? But if you have an application that's really, really heavily used, you're probably better off moving that off onto a CaaS or onto some other type of just architecture or just running a standard VM, right? But of course, the main problem with Cloud Functions is that as a developer community, we haven't figured out how to weave together Cloud Functions and manage multiple or hundreds of Cloud Functions effectively. Right? When we're writing code and we're building, let's say, even if it's a microservice, but let's use monolith, right? We're doing integration at the code level. We write code, that's how we glue together different parts of the application. It's all running in one server or whatever, right? When you're running Cloud Functions, you have to go out over the network, and then now you have all these Cloud Functions, and what if you make a change in this one over here? How does it affect these other Cloud Functions, et cetera, et cetera? That's stuff that we haven't, basically we're doing integration at the module level and not at the code level when we use Cloud Functions. So this is not a panacea either. It can get very complex and it can end up costing you more in terms of cloud. All right, so a couple more things in terms of how do you save money. Does anybody run on Graviton or ARM processors in production? No, nobody's using any of the ARM-based VMs that you can get like on Amazon or Azure or even GCP. No? Well, it's interesting. Well, maybe this will help, help steer you in that direction. So Graviton is 50% plus less expensive than x86 for compute. Right? That's quite a bit when you think about it. Okay? And we have an optimized version of Prime that is 26% faster than OpenJDK running on Graviton. So you can see by just moving to Graviton, you potentially can save quite a bit in compute. And then by layering Prime on top of that, you can save even more money and get like much cheaper compute than using x86. So I didn't know this until a few months ago when I was looking at it. I was like, wow, that's amazing. Why don't more people use it? Actually, that's a good question. Why don't you use ARM instead of x86? Yeah.
Is that cheaper because nobody's using it?
No, that's a good question. The answer is it's not cheaper because nobody's using it. It's because of the underlying CPU architecture, right? ARM is just more memory efficient. That's why, where's my phone? That's why this thing runs on ARM-based architecture, right? What's that? And your Raspberry Pi, yes, exactly, right? So that's why people, that's why ARM is good for this. Yeah. So anyways, it's worth looking at, you know, if the people at your company are really trying to say, okay, we have to cut costs. Without giving up anything really, ARM can be a little bit slower, but again, it depends on how it's sliced up by the cloud provider in terms of CPU cycles. I mean, it's pretty easy to win, right? Unless you're running, doing JNI. What's the new thing called? Making native calls in Java. Not JNI. Is it JNI?
Foreign memory.
Yeah, yeah.
FFM.
But is anybody calling like the system libraries directly from their Java code in here? Probably not. What are you calling, just out of curiosity?
C or C++.
Right. So it's some in-house library, et cetera, right? Okay, right. So in that case, you may have actually you could probably build that if you're using LLVM. You could probably build it for ARM as well, right? So anyways, I think this is a great idea. We've told some folks to use this, and they've seen substantial improvement in how much they're paying for compute in the cloud. So All right, so here's another thing. This is more of an architectural thing. Right? How many people are using managed services in the cloud, like managed Kafka on AWS, for example? Anybody using? Let me ask a different question. How many people are using Kafka on production? Okay, so about 10% of the folks here. All right, so when you use a managed service like managed Kafka on AWS, you end up paying more for it. So the question as a senior developer or an architect that you have to ask yourself is, depending on how big my Kafka deployment, I'm just using Kafka as an example. It could be anything. It could be, you know, if you're using like Apache Beam or any of the other big data platforms, Cassandra, et cetera, right? Is it more expensive? Is it cheaper for us to not use managed services, those managed services, and just do it ourselves and manage our own Kafka or Cassandra or whatever instance, right? I don't know the answer to that question. How much does a software developer cost? How many of those people do you need? How big is your deployment? All those kinds of things play into that, okay? All right, so finalement, good luck. This is, unfortunately, this is not something where there's a silver bullet, as we say in English, or a magic that you can, you know, sprinkle some magic on it and all of a sudden you have lower cloud costs. But hopefully I've given you some ideas on, you know, I like the ARM thing. Doing auto provisioning with something simple like CaaS, I think, is a good idea. Thinking about in your specific application, does it make sense to switch the garbage collector? Should I just switch the JIT off? Should I look at an advanced thing like Azure Platform Prime to, you know, offload the JIT and other things like that? So finally, how many people have heard of Fuje? This is a website for where a lot of Java stuff happens. Anyways, this is something that we sponsor as part of our community effort. It's free to become an author. If you want to, you can get in touch with me and I can put you in touch with Yurchan, who lives in Amsterdam, actually, and he can get you set up with an account and guide you through the first few things with that. So anyways, I'll make these slides available so you can click on the links and read that research paper from Google if you like, and some of the other stuff. Actually, before I forget, there's something interesting that came out of Google about a year ago. They did a research project with the University of Sydney, I believe, where they came up with a new garbage collector algorithm called LXR. Has anyone seen that or heard of it? Right, it's experimental at this point still, I think. But basically what they tried to do with the LXR garbage collector is they tried to keep garbage collection pauses to within 10 milliseconds. So what happens is, in a specifically in Java, you hit a garbage collection pause. Depending on how much memory you're using, it can be very long and could cause disruption and use a lot of CPU at that specific time. The LXR algorithm basically just does 10-second pauses. So it's a really interesting research paper on that. And of course, they open sourced everything, so you can pull it down and actually build it and try it out yourself if you want. So, okay.
So then you sacrifice throughput, right? For
With the LXR? They're sacrificing a little bit of throughput for more stability over time. All right, so instead of getting a pause where everything is just shut down, it's like pause, pause, pause. So your load doesn't look like this. It looks a little bit more flat like that. So yeah.
Isn't it quite similar to what Shenandoah is trying to achieve also?
Yes, it's similar to what Shenandoah is trying to achieve as well. That's right. So, but it's interesting that they're obviously their idea behind that is kind of what we're talking about here, right? Is how can we get stable loads without having to over provision and all those kinds of things. So, okay. All right, I think that's pretty much it. Any questions, thoughts, concerns? No? Does it all make sense? Did anyone get at least one useful thing out of this?
how do you instrument? I mean, how do you measure? You know, how much the thing is costing you?
Right.
Because if you can't measure, then I mean.
Okay, so when I work with customers, the way that I measure this is I look at, or what our field engineering team at Azul, what we do is we look at the utilization of the server in terms of CPU, right? Let's just talk about compute because that's the easy one, right? We look at the utilization of compute and compare it with what the load is like at that time. Okay, so when the thing that we're trying to achieve is we're trying to get very little extra overhead or over provisioning, right? As small as possible. So we look at what does the load look like over time, and what's the delta right above that, right? How much difference do we need there? But the way that's done is it's fairly straightforward. You fire up a test instance, or maybe just use a production instance. You put some instrumentation in on that if you need to, right? You don't want to use like a profile or anything because that adds overhead, right? So just looking at standard statistics like, what's the CPU load, and you overlay that. You overlay the CPU load with what does the actual number of requests coming in to the application look like, and that gives you pretty much everything you need to know in terms of what's the next step there, right? Should we add a little bit more memory and push that harder? More vCores, more memory, can we push it harder to add that extra load, or do we need to go distributed and try to do auto scaling and whatever? So it all depends on that, I think, so, okay. Okay. More questions? Okay. All right. Well, thank you for having me. I hope you enjoyed the session.